So the second application of the vector equation that we can use is application to kinematics, speed, time, and velocity. So a little bit of review. We already know our vector equation line, where you've got r as any point on that line, so we can write that as any position vector on the line. A is a random point on the line, so we can write that as a random position vector on that line. And then B is your direction vector. And T is a scalar that just says how far in that direction you need to go. So now, with speed, time, and velocity, r is the position of any point on a path. So some object is moving along a path. Okay? A is where that object is starting. And B becomes your velocity vector because it has a direction and a length, and that length will be its speed. So we'll see some examples that deal with this, but it means that if an object moves, if your direction vector is 2, 3, that means in 1 unit of time, it's going to move 2 in the x direction and 3 in the y direction. And however long that is, the hypotenuse of that triangle, that'll be how far it's moved in 1 unit of time. In other words, its speed. So here's an example. We got a moving object. It's starting at 1, -1. And its vector equation is r equals 1, -1 plus t, 3, 4. We're dealing in kilometers here, going east and north, and time is in hours. So our velocity vector here is the 3, 4. And if we figure out the length of that, basically what's happening is in 1 unit of time, so when t is 1, it's going to move 3 in the x direction and 4 in the y direction, giving this resultant, which as a 3, 4, 5 triangle, that will have a length of 5. So it's going to travel 5 in 1 unit of time. Since time is in hours and the units are in kilometers, there's your speed, 5 kilometers per hour. So just describing this in words, the object starts at 1, -1, and moves in a direction of 3, 4 at a speed of 5 kilometers per hour. And then part C is just practicing switching from the vector equation of the line form to the parametric forms to the Cartesian forms. So if we write our parametric forms of just the x and the y coordinate, then we can solve for t and get them in a Cartesian form. And from that Cartesian form, you can just rearrange things, multiply both sides by 4, both sides by 3, until you get it into the form that they're asking for. So here we have another example. This time we're giving the parametric equations instead of the vector equation. If we have the parametric equations, can we write down the vector equation? Yes, we have a starting point at 4, 5. 5, -2 is your velocity vector. Now, personally, I like this first equation. That's my favorite form of the equations, but you could write it with the i's and the j's as well. So what's our velocity vector? The 5, -2. And then you just do a squared plus b squared equals c squared. And you can get the speed. So this object is going, I don't know, through the air, or it's running along the ground, and there's a pole located at 39, -9. Will that object collide with that pole? So what we're basically asking is the point 39, -9 on the line, or is it not? And as far as our vector equation line goes, we're asking if this 39, -9 can go in for that value for r. If it does, there has to exist a time t that makes that work. So when we set that up and we solve for t in the first equation, we find out that t is equal to 7. And when we solve for t in the second equation, we find out that t is equal to 7. So since that's consistent, at 7, is it seconds in this one? Yeah, at 7 seconds, it will hit the pole. Here's our next example. A jet is flying at a speed of 700 kilometers per hour in the direction of 2, 6, -3. What is the velocity vector? So a velocity vector has a direction, but its length is also its speed. So we know that our velocity vector has to be the same direction as this 2, 6, -3. But if we measure the length of 2, 6, -3, it won't be 700. So then we need to maybe find the unit vector we could and then multiply it by 700, or some other way to make sure that we have a vector in the same direction that has a length of 700. So when we find the length of the direction vector u, we find out that its length right now is 7. So this example does lend itself to a shortcut because the numbers are nice. Its length is 7. We want a length of 100. What should we do? Multiply by 100. So if we would multiply that direction vector by 100, we would get that. Now, that works out nice here, but let's say the same question came up and it wasn't 700, it was 585. And you're like, that does not work out nice with 7. Then you could find the unit vector and then multiply from there. So here's our unit vector. And a unit vector would have a speed of 1 kilometer per hour in that same direction. And then you just need to multiply that by 700. It has the same direction as the vector that we started with, and it will have a magnitude of 700, so its speed will be 700. We've done so far speed of the yacht. That's just your velocity vector and the length of it. All of a sudden the yacht changed into a pleasure boat. Not on yours. So there's our cargo ship. At time 0, it's at 6.3. At time 0, the yacht's at the origin. So you can just figure out the distance of the vector 6.3. is 45 kilometers. So now, this is something that's a little bit different than our intersection thing that we've done before. Because in our intersection of two lines, our parameters were often one was t and one was s. I think one time we had t and lambda, because we're just trying to find out if two lines intersect. Now, two lines can intersect as long as they don't intersect at the same time. They're going to be fine. It's just when they intersect at the same time that you have a problem. So notice now in our equations here, we're using the same parameter, because parameter is time, and it's the position with respect to time for both of these that matters. So when we solve our parametric equations and put them together, can you see that the x-coordinate in the first equation would be 5t, the x-coordinate in the second equation would be 6 plus 3t. If you solve for t in both of those equations, you get t equals 3. If you got a different value of t in the first equation than you got as a value in t in the second equation, it would mean that they don't cross the same point at the same time. They still might cross paths, but they just won't cross paths at the same time. But here they collide after 3 hours. Should have been paying more attention on that cargo ship. So again, we've got our standard vectors 1, 0, and 0, 1 as kilometers, and north and east. There we've got a circle of radius 25 with center at O, and the lighthouse is right at that origin. Okay? So anytime you're outside of that circle, you can't be seen by the lighthouse. So a ship is currently at -31, -32. The ship is moving parallel to the vector 4, 3 at a speed of 20 kilometers per hour. Write down OP. That would be the vector -31, -32. Now, part B is actually more difficult than it seems, because in part B, the most common student error is that you want to use this to show that it works. Okay? If you're trying to show that this is the equation, you can't use any information in that equation unless you know it from somewhere else. So as soon as you use what you're trying to prove something, that's a circular argument, and that won't get you the marks that you would want for this show that question. So what do we have? We know that this is our equation of our line. And we know what each of those things stand for. Starting point, R is all points on that path. There's your velocity vector. So what do we know already? We know a direction vector, but that's not our velocity vector. In fact, the length of that direction vector is 5. So if we want our velocity vector, since ours has to have a length of 20, a couple of things you could do. You could make a statement saying, since ours is a length of 20, you need to multiply by 4. Or again, you could find the unit vector like we have here, and then multiply that unit vector by 20. And then you'd find your velocity vector to be 1612. So it's not okay just to show that the 1612 has a length of 20, and the 1612 is the same direction as 4, 3, because then you're using the 1612 to prove the 1612. You have to come up with the 1612 on its own, starting with what you know, and then you can say that this is my equation. So OR is after 1 unit of time. And then PR will just be the vector R minus the vector P, which makes sense that it's going to be 1612 because that's what you're traveling in 1 unit of time. So now we want to show that when that ship reaches R, the lighthouse first becomes visible. Well, we know that our R is at negative 20. The lighthouse is at 0, 0. If we figure out how long that is from 0 to R, or from the origin to R, we find out that it's at 25 kilometers, which is exactly the radius of the circle where things can be seen by the lighthouse. So that's when the ship first becomes visible. Not sure if you've noticed a pattern in the notes at all, but there's another ship on another path. Will they collide? So here we got our two equations. We've got a different unit here for S. I think we'll solve it this way. Normally we would set things up so the time was the same time unit. But since this is set up with two different variables, solving for that, creating your systems of equations, and solving those systems of equations should have got t is equal to 4 and s is equal to 4. Now technically, I think this was a typo originally. I think I wanted to have both of them in terms of t because they'd have to collide at the same time. But when we solve it, we notice that they do collide at exactly the same time at 4 and 4 anyways. So because both of those are at 4, they will collide at a time of 4 hours at the point 3316. I think when I originally made these notes, I was thinking about playing with my toy cars as a kid and how you always like to crash them into each other. So what fun would it have been if there would have been like, oh, a narrow miss. If we're going to make a question, we may as well make them collide. And that is the end of vectors.